Okay, for my 460 for my students on Zoom, could you raise your hand if you can hear me and see my screen? Okay, perfect. And could someone just unmute themselves and try talking? I want to make sure that I can actually hear.
Hello.
Perfect.
Hello.
Okay. Yep, we're good. Okay.
I actually have a question if
Yep.
you don't mind.
Yeah, go ahead.
For question 2 on the homework part D, it asks us to make sure date from and date to must be greater than today's date. But it looks like MySQL doesn't allow current date to be used in a check, and it keeps giving me an error. I'm not sure a workaround for that.
Okay, just a second. So, whoops, wrong course, sorry. You're saying which on homework 4? I'm sorry,
Question 2,
4.
part D. Is that 2 part D? The date from and date to must be greater than today's date.
I also had this issue.
Okay, date from and date to must be greater than today's date. Okay, let me, a second, I'm going to stop the screen share for a second. And just going to check what I did.
If this D, it says to comment it out when you're doing it since it won't work in MySQL.
That might be it. It might be that
it says parts A through D can be all be written using
because
check
I did a check. Okay, so assume that you can use current date on the right-hand side. That's what I did, and to be honest, I believe that was, I took this answer from the previous textbook, so I'm pretty sure that in SQL you are allowed to use current date. And it just may be that I guess I don't understand. I can use current date in an inequality now that I'm thinking about it. So how are you running into this issue? You're saying select. Are you just
From
using
what
a
I
check
found, so
command,
it's
or?
inside of the check. Yeah, it's inside of the check, and it's saying that you can't use like current date, the function inside of a check command.
Okay, I think, okay, just ignore it and pretend you can. I think, I haven't been able to check this yet, but someone else said it appears the check command is now working in MySQL. And in previous instantiations of this course, the check command was not yet working. It was only being syntactically parsed. So it may have to do with MySQL now implementing the check command, but maybe not providing full functionality for it. I will check into it, but bottom line is I will accept an answer where you use current date in an inequality, okay?
All right, sounds good. Thank you.
You're welcome.
I have a follow-up question.
Did you get that, Michael, too? Okay. Okay. Yes, go ahead, Jordan.
So let's say that condition was in the table. What would happen when somebody tries to insert something? Would it then check every existing element as well and fail if there were any that failed that condition?
Only do it on the new tuple. So if you say that you have a check and you say that the current date has to be less than or equal to date from, it's only going to apply it on the inserts. So the check command is only invoked when you try to insert a new tuple into the relation. It's not re-invoked every time. It's not periodically invoked and say you remove tuples that no longer obey that check command. It's only executed once on insert.
And it only checks the thing being inserted, not the entire
Yes.
table.
Yes, it doesn't check the rest of the table. Now, a constraint is different. A constraint, no, it's the same way. It's only executed on an insert or an delete. It's not being applied any other time.
But if you were to write it, say, as like a if exists select from table where the date is less than today, then that would fail if there's any items in the table, correct?
Run that by me again.
If you were to write it as a check if exists select from table where the date is less than today.
But it's the same thing. So if you wrote, it's only, yes, I guess if you wrote it in another table, a check command, and you said you can only insert the tuple if there does not exist a tuple in the booking relation that is, that the only tuples that exist in the booking relation are essentially greater than the current date, but that just wouldn't make sense to write that kind of constraint.
Right.
But
That's what I was thinking as well.
You could write something like that. It would, I mean, you can write anything you want. It's just, obviously you don't want to write constraints that are going to tie your hands. But the important thing is these constraints are only executed on an update command. They don't apply to tuples that are already in the database. So they're not retroactively applied, so to speak. That's the important thing. Okay.
Thank you.
Any other questions before we get going?
I have a small one.
Mm-hmm.
Okay, so it says, I think it was in number 2 that on an update, so on update and on delete, does that mean that we need both an on update clause and an on delete clause, or can you accomplish that with one?
You need both. You need to say on
Okay.
delete, on update.
Okay, thank you.
One thing I forgot to mention in class is that when you try to apply a foreign key or create a foreign key constraint, it will fail if you have not declared the key in the parent relation to be a primary or unique key. So if you try to say, for example, that in the property for rent relation, that its staff number is a foreign constraint that references the staff number in the staff relation, you will have to have declared the staff number in the staff relation to be a primary key or a unique key in order for that foreign key constraint to go through. Otherwise, MySQL will reject it.
I have a question about that.
Mm-hmm.
So in number 2, it says to recreate the booking table, the guest table, and the room table.
Mm-hmm.
But so if we have
I
to
guess you
create a
have to
primary
create
key
the
in,
hotel table, right? Based on what I just said.
yeah,
You're going
that's
to
what I
have to
was,
create a hotel table.
that was my question.
Yeah.
Thank you.
Sorry, it did not occur to me until you asked the question that effectively I'm forcing you to create a hotel table. Just make it minimal for the hotel. But yeah, I'm forcing you to make a hotel table, it turns out. Other questions? The reason hotel wasn't in there, I always meant for you to create a hotel table. I didn't realize that the previous question said create a hotel table, and then this question just said create it for the 3 tables. And so that was kind of what got messed up. So I need to change that and say you also need to create a hotel table. Other questions? Okay. Couple housekeeping things. So first of all, for several reasons, I'm going to have to take the class online for the next few weeks. I plan to bring it back on in person or online in a few weeks, but I'll let you know when that happens. Also, I realize that the office hours I set have not been particularly practical for me. So I'm resetting them from Monday to be 2 to 3 p.m. and Tuesday to be right after my second class. I teach again after this class. So I'm going to set them from 2:45 to 3:45 on Tuesday. Originally, I thought I'd grab lunch between my second class and office hours, but it turns out it's just too tight of a window. I'm just not able to fit it in. I'm rushing around, and I'm still getting to office hours about 10 to 15 minutes late. So I'm just going to move it and bite the bullet and not have lunch until after that time. So I will post these new revised office hours later today. And then what we're doing today, we're finishing up the relational calculus, and then we're moving into entity relationship design. So how we actually design relations given some description of a problem. So just as a reminder, the relational calculus forms the formal foundation for the data manipulation language in SQL, basically for the CRUD operations, create, read,
Dr. BVZ,
update, delete. Yes?
you're not sharing your
Oh,
screen.
I'm not sharing. Thank you. Whoops. Thanks so much for telling me that. I forgot that I was no longer sharing. Okay. Now can you see the screen? Is it possible to see the screen?
Yeah, we can
Someone?
see it.
Yeah, we
Okay,
can.
great. Okay, so here's what you missed. I basically had written down the revised office hours here, which I will post, and said that we will be going over the relational calculus and ER design today. Okay. So relational calculus forms the formal theoretical foundation for SQL's data manipulation language, and in particular for the where, how you specify the where predicates for the various create, read, update, and delete. So I'm going to skip ahead to where we were. Okay, so as a quick review, basically what we're going to be doing with specifying predicates. And we're going to have tuple variables where the tuple variable ranges over each tuple in a relation. We substitute the values for that tuple into the predicate. If that predicate becomes true, evaluates to true, then that tuple gets added to our result set. And the reason we call it the tuple relational calculus is because we are basically having our variables, our predicate variables, range over tuples. And the way we write a tuple variable is we specify the name of the relation and then the name of the tuple variable. And then This query looks like a set with the attributes that we want to appear in the result on the left-hand side of the bar and the right-hand side giving the predicate over that particular tuple variable. So as an example, if we want to find all details of staff where the staff salary is greater than 10,000, we say, give us a set of tuples in S such that S ranges over staff and S dot salary is greater than 10,000. If we just want the salary attribute, then we can specify a comma separated list of attributes on the left-hand side. Hey, and I did say that you can generally, if you're having difficulty writing the relational calculus query, you can write a corresponding SQL query. So here's the corresponding SQL query for getting staff whose salary is greater than 10,000. And basically, anything that appears in the select statement goes on the left-hand side of the vertical bar. So you copy this part down to the left-hand side. Anything that's in a from clause becomes a tuple variable. Tuple variables are separated by the and sign. So if you have a multi-table query with multiple tuple variables, they're separated with an and sign. And then the where predicate is appended with an and sign. So you basically take whatever is in the where, you append that to the tuple variables with an and. Okay, so then went over a number of I guess relational algebra operations and how you'd express them in the relational calculus. So here's how you express Cartesian product. It's essentially it's just a select R or select R dot star. Well, let me show you. Cartesian product. If you wrote this in a select statement, it would be select R dot star S dot star from R comma S. Now, if you do it as tuple variables, you can also say select T1 dot star T2 dot star from R T1 S T2. It's the same deal. So that's how you can get Cartesian product. There's just no where clause specified. Okay, here's a join. So a join, you now have a multi-table query. So there's two relations, as you see, the tuple variables separated by an and then the where clause being a equality on the two on the join attribute. Okay, this is where we stopped last time. So we've caught up with where we were at the end of the last lecture. So the relational calculus has two quantifiers that you can specify to say how many instances the predicate has to apply to. So if it only has to be true for one tuple in a relation, you can say there exists. If it has to be true for all tuples, then you say for all. And we say that any variable that is qualified with a for all or exist is a bound variable, and otherwise it's a free variable. And this is very important right here. Only variables to the left of the bar may be free variables. So only free variables are allowed to be to the left of the bar. And there exists and for all essentially forms the basis for subqueries. But they're also the only way that you can implement certain joins, as we will see in a moment. So here's an example using the exist. So it's a semi-join. We want only the names from the staff relation, such that the staff member works in the London branch. So basically, we want to do a semi-join of the staff with branch, such that b.city equals London. And we actually have to do it in the relational calculus using a subquery. And here's the way we do it. There's staff S, and there exists a branch B, such that the branch number matches the staff's branch number, and the branch's city is equal to London. So that's an example of a semi-join implemented essentially using a subquery. Here's an example of a for all. So we're saying for all B, B's city is not Paris. So this would essentially, we might use this in a check clause to say that we can't have any branch in the city of Paris. So that would be a way to write that. We also can, using essentially De Morgan's law, invert a for all. So the equivalent would be there does not exist a B such that branch B and the city is equal to Paris. So remember, with De Morgan's law, basically inequalities get changed to equalities, you negate them, and the for all gets changed to it that does not exist. Okay. So those are the basic operations. You have the, well, let's actually quantify what are the basic operations. You've seen examples. Now we're going to quantify what you can and can't do. So we talk about a well-formed formula, which is essentially a predicate. So think of a well-formed formula as a predicate. So it can be a tuple variable that ranges over some relation. It can be a relational or Boolean operator that compares two attributes. Okay, and Boolean operators and, or, and not. It also can be a comparison with a simple constant. So those are your so-called atoms, your most basic formula. Then you can connect them using conjunction, disjunction, or negation, which is simply and, or, and not. Or you can use the there exists or for all and put that in front of the formula, in which case you're binding the tuple variable. Okay, so it's pretty simple in terms of what you are able to do. And here I kind of set out what you use things. So Boolean operators, and actually I should have said probably relational operators there, are typically used for select queries. Then I already showed you an example of a semi-join. So there exists F is typically used for semi-joins. The not exists F and for all are typically used for integrity constraints. So you might say all staff members must like less than 100,000, or there does not exist a staff member who manages more than 100 properties. And then the final thing is that you also use there exists and for all to form subqueries. Okay, so I have now a whole bunch of examples that hopefully make this a little bit clearer. So let's say you want to do a union where you get the cities that are either in relation B, the branches, or the properties P. So you can say that that is the set of cities in T such that T ranges over branch or T ranges over property for rent. Okay, if we want set difference, it is the whatever is in B that is not in P. So we want the set of, what we're saying is we want the set of branches that do not manage a property in that city. So we're saying B will range over branch, and there does not exist a property for rent such that the property is in that particular city. So if this condition is met, that's a city will end up in this result over here and will end up being printed out.
Dr. VZ,
Yep.
at the top, what is the T dot city? What's the T there?
It's the tuple variable. See how T ranges over branch? So for each, what it's saying is for each tuple in branch, each tuple will successively be bound to T. So then what we're doing is saying, okay, in the result, we want the city attribute from T.
Tuple from the union.
Yeah, so what we're saying is, so we're saying we take any tuple, actually this should have been an and, because that's how you, no, actually it should be an or, I take it back, it should be an or. So it is, you're saying for each T, I'm sorry, for each tuple in, okay, let me write it out. When you have branch T, what you're saying is for each tuple, an element, or for each tuple, an element of branch, T equals tuple. If tuple or T satisfies predicate, okay, add T dot city to result. Okay, and since there is no predicate, it automatically satisfies, it's true. The predicate essentially is true. So T automatically satisfies the predicate, so T dot city is added to result. So that's essentially what this is saying is T ranges over each tuple and branch. If it satisfies the predicate, we add it to the result set over here.
Okay.
Make sense or not?
Yeah, I was just because I saw the B and the P down in the other examples, and I saw T, I was like,
That's
T?
because here you
Anyway,
have to
okay,
have
yeah.
a way of having the tuple variable range over two different relations. That's not necessary in any of the other queries we do. Union's kind of hard, is kind of a hard thing to express easily in the relational calculus.
Okay, thank you, appreciate it.
Okay. Okay, so for intersection, it is the set of cities that are in both B and P. So we want the set of cities such that B is in branch and there exists some property such that B dot city is equal to P dot city. So again, this is a semi-join because we're only taking elements from B, but we're joining branch with property for rent. So intersection can be, in this case, implemented as a semi-join. Okay, set division, a little more interesting. So I'm assuming this is our park example that I want all parks, I want to list the tourists who have visited all parks in Tennessee. And I assume I have a tourist relation with tourist information, the tourist name and their address, a park tuple with or relation with information about each park. And this actually includes information about parks, not just in Tennessee, but any state in the country. And then a visit relation that gives the name of a tourist and the park they visited. So now we want to list the tourists who have visited all parks in Tennessee. So what we're going to do is we're going to let T range over each tuple in tourist. And then we're going to check the and is going to give us a predicate that checks whether that tourist has visited all parks in Tennessee. So we say for all parks in the park relation, either the state is not equal to Tennessee. So we don't care about any park not in the state of Tennessee. So that's the first part of this, is we're essentially, this clause right here says, okay, ignore any state that is not Tennessee. So either the park is not in Tennessee or there exists a visit such that the tourist name is equal to the tourist name in the visit relation, and the name of the park visited is equal to the park name. Okay, so this is essentially a join of T with V with P. This part right here, actually. Right. Okay, so this part right here, what this really is simply T join, natural join with V, natural join with P. And what we're saying is that the result of that join, okay, and we have some tourist name. So basically we're saying there exists a V such that with whatever tourist we currently have, that tourist right here is bound to some name right now. So if that tourist name can reach into a visit relation, and then that what it extracts out, that will extract some number right here. This right here will give us the set of all parks visited by this tourist. Okay, and now we are specifically saying, okay, does that match the particular park we're looking at? In this set of parks, in this set, is there a park that matches the current P? So as I say, what it is really is a three-way join. Now you may have to stare at this a little. Again, I don't claim this is an easy one to figure out, but it is the way that you would express set division in the relational calculus. And again, this part's really important. This part right here throws away any park whose state is not in Tennessee, because we don't care whether, we're not asking for tourists who have visited every park in the country. We're only asking for tourists who have visited every park in Tennessee. So when we encounter a park whose state is not equal to Tennessee, it's automatically true. We say we're not going to consider it further. Okay, so questions about set division. Okay, so then moving on to some different operations we might care about. How do we get a left outer join in the relational calculus? So let's say we want to list students and the courses they are taking and include all students in the result, even if they are not taking a course. So that's a left outer join of student with enrollment. So we want the names of all students and the courses they're taking. So we say, let S range over student and E range over enrollment. So this is a join and both variables are free here. And SID equals E dot ID. So this gives us, this first clause gives us all students who are taking courses. The second clause is going to give us all students who are not taking courses. So the second one says, or give us students, S, and there does not exist an enrollment tuple such that S.ID equals E.ID. And in this case, you would get a null for E.course ID. So the first one gives you all students that match a tuple in the enrollment relation, thus giving you all students taking a course, then or with all students not taking any course. That gives you a left outer join. Okay, and now just some more examples of things. Here's list the names of all managers who earn more than $25,000. So it's a query that involves a conjunction of position equal manager and salary greater than 25,000. Okay, list staff who manage properties for rent in Glasgow. This is a semi-join. Why do I know it's a semi-join? Because I'm going to have to join the staff with properties for rent, but I only want staff in the relation. I don't actually care in my result to have any information from property for rent. So it's a semi-join. So again, the unbound variable is staff. The bound variable is property for rent. We want all staff who manage a property in Glasgow. So there must exist a property in the city of Glasgow such that the staff member's staff number matches the staff number managing that property. Okay, if you're looking for the comparable SQL query, written verbatim from here, you could write the SQL query as a natural join. But if you're writing it verbatim, from what you see here, this is what it looks like. From, select S dot star from staff, where exists, select star from property from rent. So that's what this does. You're ranging over every tuple in property for rent where P dot staff equals S dot staff number and P dot city equal Glasgow. So that's a literal translation of this relational calculus query into SQL. You don't have to write the query like this in SQL. You could just write this query instead. Let's see, actually, I might have it in the next slide before I spend all my time. Nope. Okay. So I could write this also as select S dot star from, we put it down here, from staff S natural join property for rent. I'm going to abbreviate it here so I don't run out of screen space. Where P dot city equals Glasgow. So that would be another way to write this query in SQL. Okay, and so here's the seemingly comparable query because I said, okay, I just showed you the comparable query in SQL using a natural join. So you say, okay, I want to do it this way. And it's like, looks like a natural join and property. So it's staff S and property for rent P and P dot staff number equals staff number and P dot city equals Glasgow. But the problem is this property for P makes it a free variable, even though P is not on the left side. So technically, that makes it not a valid relational calculus query. So you actually should not be writing the query like that in the relational calculus. And it's because P is a free variable, but if it's a free variable, it's supposed to show up over here, and it doesn't. So if I did want something from P, so if, for example, I wanted the list of all staff who manage a property in Glasgow and I wanted the address of that city, then I might write S comma P dot address, then it would be okay to write the query this way. Okay, I know it's technicalities, but technicalities are important. Okay, so here we want to list each property that rents for more than $450, list the name of the staff member who manages the property. So now we can write it as a join because we want stuff from both the property and we want the staff name. So now it's just a straight join on the staff number and property for rent greater than $450. Okay, so here's one where we want to list all staff who do not manage any properties. That's probably not good. Maybe they're not being aggressive enough. We need to have a talk with them. So in this case, we want any staff member such that there does not exist a property, such property for rent, and the property for rent's staff number matches that staff number. And notice I can also write it as a for all. I could say staff S, and for all properties P, the staff number is not equal to the property staff number. Either way is fine. Okay, and then this is a three-way. I believe this is a three-way. Yes, this is a three-way join, but it's still a semi-join in the sense that I only want to see the results from the client. So I want to list the name of clients who have viewed a property for rent in Glasgow, but I only care about the client. So I'm going to have to make V and P. I'm going to do a join of C with the view and property for rent relations, but since I only want details from the client, client's the only free variable, and I've bound V and P. So I'm saying there exists a V and there exists a P such that the client number matches a client number in the viewing relation, and the property number associated with that tuple matches a property number in the property for rent whose city is Glasgow. So this is a three-way join between client, viewing, and property for rent, but it is a semi-join in the sense that I only want the result to include details from the client.
Dr. VZ,
Yes.
I might have misheard you, but did you say C was a free variable?
Yes.
Yeah, I thought the ones that were on the left were bound, and then the
No.
ones further on
Bound
were free.
variables
Am I
are
misunderstanding
ones that are bound by an existential quantifier, either there exists or for all. Free variables are ones that are not bound. Let me go back. I need to go back a bunch of slides. Here we go. This is the important thing. Tuple variables qualified for all or exist are called bound variables. Otherwise, they're called free variables. Only variables to the left of the bar may be free variables.
Oh, okay. Okay, yeah. Thank you. Sorry about that.
No worries. Good to ask the question. Actually, I appreciate, because we want to make sure it's all clear. Any other questions about that? Okay. So the last thing is you have to be careful about expressions that could generate an infinite set. So you don't want to be able to write this query, the set S such that it is not in the staff S, because that's an infinite result. It means essentially return any person who we don't employ, but that's definitely not in the database. So to avoid this kind of nonsensical query, we add the restriction that all values in the result must be values in the domain of the expression. So in this case, S can only range over the tuples in staff. So the answer is there is no tuple in S or in staff that satisfies this predicate. Therefore, this would actually be the empty set, because we're restricting the result to be only tuples that are in the staff relation. So that prevents us from getting into situations where we're essentially being asked to generate data that is not in the database. So, questions about that? Okay, this is some of the heaviest material that we cover in the entire course. What we're moving into is perhaps easier to understand, although it's going to take you some time to learn how to apply the principles. So what we're moving into is essentially if you are given a description of a problem, then how are you going to design a database to model that problem? So for example, the property management case study in the book, there's some verbiage that says, okay, we have staff, we have branch, staff manage properties, there are leases on the property. So you basically, in the real world, you might be called in and you're going to be asked to create a database, often from scratch, and you're going to have to figure out, okay, what are the relations or tables? What are the attributes? And what are the relationships between those entities that we identify? So there's two ways you can actually design a database. One is top down, which is almost always the way you design a database. And the principal method used for top down design is called the entity relationship modeling. Then there is a bottom up approach called normalization, which we'll cover next week. And it is more often used as a check on the tables that we generate using ER modeling. So typically most designers start with a top-down approach and come up with a set of tables, and then they use normalization as a way to check to make sure that the tables have been properly decomposed, because we want to avoid having redundant data in our database, because that can lead to inconsistencies. And if we just design stuff top down, we can somewhat naturally create redundant data. I know I'm talking in some generalities, so what I'm going to do is move into how we do ER modeling, and then when we get to normalization, you'll see what I mean by why we may use it to try to ensure that we have no duplicate data sitting in the relations that we created using ER modeling. So the objectives for this lecture, which we'll swap probably into the next lecture, is give you the basic concepts associated with the ER model. Then there's a diagrammetric technique called unified modeling language. So it's a picture language for drawing a entity relationship model. And then there's two common problems called connection traps that you get with ER models, and we look at how you identify and solve them. So there's really just three concepts to the ER model. There are entity types, which are physical things that exist, like staff, branch, properties. There are relationships between these entities, which are represented as foreign keys. So the lease relationship is, leases are a relationship between properties for rents, owners, and clients. Or we have staff that belong to a branch. So every staff tuple has a branch number indicating the branch at which that staff member works. That's a relationship between staff and branch. So relationship types boil down to foreign keys. When a relation has a foreign key, it indicates there's a relationship between that relation and some other relation. And then, of course, we need to identify the attributes in any entity or any relationship. Okay, so first thing, entity, a group of objects with the same properties, identified by a business as having, or organization as having an independent existence. So they can have a physical existence like staff, property, customer, product, supplier. Honestly, I no longer view these as entities. So a viewing is really a relationship between a client and a property. A client views a property. A sale is generally a relationship. A customer buys a product from a supplier. So I need to update this because when they talk about, the previous textbook used to talk about conceptual existence of entities, but really every single one of these is more like a relationship between physical entities. So I tend to think of entity types as having some kind of so-called physical existence. And the way they're displayed in UML is as a rectangle labeled with the name of the entity. So this is how you would do it in a so-called ER diagram. I will call them ER diagrams. You might hear them called UML diagrams. It's the same thing. So then a relationship is a meaningful association among two or more entity types, and they're represented in relations by foreign keys. In an ER diagram, they are shown as a line between two entities, a directed line, and the relationship name. So in this case, we say branch has staff. Do we have rules for it? Nope. Okay. Some rules for relationships. Try to use action verbs as much as possible. I know here has is not an action verb. Perhaps employs would be a better verb. So try to employ action verbs if possible. 2 is don't reuse relationship names. Use unique names. Okay, let me write this down because it's important. So with relationships, one, try to use action verbs or active verbs rather than passive verbs. 2, use unique names. So don't repeat relationship names. And the reason is it gets ambiguous. If you're discussing a design with some coworkers and you've used duplicate names for a relationship, then it's ambiguous as to what you're talking about. Okay, and they are, let's move on before I'm going to come back to this slide, but so you can see there is a directed line here. So we talk about the degree of a relationship is the number of entities participating in the relationship. So a binary relationship has 2 entities participating in it. A ternary one has 3, a quaternary one has 4, and so on. If it is a binary relationship, you put a direct edge between the 2 entities, and it should be a directed edge. And we'll talk about how you direct how you direct it in a moment. Okay, so you're obviously have 2 choices. I could direct it toward property for rent, or I could direct it the opposite way toward private owner. If it's greater than binary, so if there are more than 2 entities in the relationship is represented as a diamond. The name of the relationship is inside the diamond, and the edges themselves are undirected. So this says staff registers a client at a branch. Here's an example with the booking relationship. A guest books a room at a hotel. Another one that I don't show here would be from the property management case. You might have a lease as the relationship. It would be a client leases a property from an owner. And it might actually be quaternary if you included the staff number. It might be a client leases a property managed by some, no, then that's a separate relationship. Never mind. It'd be a 3-way relationship. It would be client leases property from owner. And again, it would be represented as a diamond like that. So undirected edges, diamond connecting the entities involved in the relationship, name of the relationship in the diamond. And again, try to use a verb. Beginners generally don't recognize relationships that aren't binary. So many of you will try to reduce relationships to binary relationships, and that's not what you want to do. So it is true that a guest has a relationship with a booking. A guest makes a reservation. It's true that a booking has a room, and it's true that a booking is associated with a hotel. But this would be completely the wrong way to represent or draw the ER diagram, because it obscures the fact that the booking is actually a 3-way relationship between a guest, a room, and a hotel. So, as I say, I know it will be difficult as you get started to recognize relationships that are have a degree greater than 2, but it's important that you start getting in the habit of recognizing those relationships, because you really don't want to end up drawing everything as a binary relationship. It completely distorts what's going on in the business or the database. So here's an example of a 4-way relationship. And here we have a solicitor who arranges a bid on behalf of a buyer, which is supported by some financial institution. That financial institution, for example, might be making a loan to the buyer. That would be a 4-way relationship. Okay, you can also have recursive relationships where the entity points to itself. And a good example of that is the manages relationship. So you may have a staff managing or supervising other staff. So it becomes a recursive relationship because it is a directed edge back to yourself. And when you have that kind of recursive relationship, you often use role names to make it clear what's going on. So here, supervisor supervises supervisee. So with these recursive relationships that point back to the same entity, you often add role names to the edges, so it's clear why you have this recursive relationship. What's going on in that recursive
Dr.
relationship?
Vandersteen,
Yes, go ahead.
when you have ternary and quaternary relationships and you're connecting things with a diamond, does it matter which way around the diamond you connect things? Like, do they need to be in clockwise order or anything, or is it just
No,
however?
okay. Yeah, so the question is, does it matter how you order, if it's a diamond relationship, a degree greater than 2, does it matter how you arrange these entities around the diamond? And the answer is no. It can be any direction that is convenient. The only thing that's really important is that the edges be undirected. A lot of you will end up trying to direct these edges, and they should not be directed in this case. That's the big thing.
Okay, thank you.
You're welcome. Other questions about that?
Is a diamond supposed to suggest that you can only have a 4-way at max?
No, it's not. But in practice, it would be pretty uncommon. I actually not sure that I've actually ever, this one is forced. That bid to me is more like an attribute of the relationship. So I think even this one that you're seeing here is a bit forced. I've never really seen anything that's more than a 3-way relationship that's natural. But that's not to say it can't exist, just that maybe I haven't dealt with complicated enough databases. I've just never seen anything naturally that is greater than a 3-way. But
Okay.
that's not to say that they don't exist. And they could be greater than, even though I know it's a diamond, and that kind of suggests the maximum you'd ever have is 4, it can be more than 4. Okay, so that was infinite, or not infinite, that was recursive ones. So then sometimes you also end up with relationships that are kind of, there's 2 relationships between entities, but they go in different directions. So here you have, it's a branch has or employs staff, but you also have a relationship that a staff manages a branch. So if you looked at this in the actual relations, what you would see you might see this. You have staff and some set of attributes, one of which is branch number. And that's the branch number at which the staff member works. But you also might have branch, and one of the attributes might be manager. But manager is actually a staff number. Okay, it's an example where we're not using the same attribute name simply because it's not as descriptive. Manager is a more descriptive attribute name than staff number. But what we have here is 2 different relationships in different directions. So staff manages a branch employs staff. And here they're saying you might have role names here. So manager manages branch office has member of staff. I'm not as picky about that one. I think oftentimes you can figure out what the different relationships are if the verb is good. But if you want, you can, when this situation arises, actually also associate role names with the two edges. I just think it tends to clutter things up. So unless I think it's really not clear what two things are involved in the relationship, then I will probably not have role names in this case. Whereas back here, I generally find that with the recursive ones, you do want to label the edges with role names because it's often not exactly clear why you have that recursive relationship. Okay, then attributes are a property of an entity or a relationship. It can be, relationships can have properties too, like the booking relation is actually a relationship and it has date from, date to associated with it. So it has attributes that are part of the relationship. A lease is a relationship, but it would have things like a monthly lease, a from price and a to price. I'm sorry, from date and a to date. Might have some other pieces of information in it. So relationships can have attributes too. And there's three kinds of relation attributes. So they're identifying attributes, which provide information that uniquely identifies an entity. There are foreign key attributes that link to another entity. And there are descriptive attributes that provide descriptive information about the entity. So I've labeled descriptive attributes as unstable because they are often updated or changed. By contrast, I have labeled keys as stable because it's pretty unusual for you to change a key. Like your social security number will probably never change in your lifetime. Your student ID number will probably never change in your lifetime. That's very stable. But other things like your age are not stable. Your address might not be stable. So things that are descriptive about an entity, they tend to be unstable. And then foreign key attributes, because they link to primary keys, they tend to be stable as well. Okay, so you can have either simple attributes or composite attributes. A simple attribute has a single component. A composite attribute has multiple components. So a date is a composite attribute because it's a month, a day, and a year. A street address, or if you have an address that is a street address, a city, a state, and a zip code, that's a composite attribute because the street, the zip code, the city, and the state all exist as independent existence, but they're being combined into a composite attribute called address. So those are some examples of composite attributes. Then you can also have single valued or multi-valued attributes. And remember, the relational model doesn't allow multi-valued attributes, but that doesn't mean they don't exist. It just means you have to figure out how you're going to model a multi-valued attribute in a relational model. And in fact, you see that I say it's typically represented in a separate relation. And I will get into that on Tuesday because we're running out of time. And then there's derived attributes, and it's a value derivable from the value of a related attribute or set of attributes. They typically end up in views. They are not explicitly stored in the database. There's three types. One that's computed from an aggregate function, like say total staff count, or it might be computed from two columns in the same relation, such as the number of days that a guest is staying in a room, or it could be computable from columns that belong to different relations. So if we want the total cost of a guest stay, that's the product of the number of days from the booking with room costs from the room relation. So 3 types of derived attributes. I'm going to stop there because I've actually talked about the 3 basic types that we have in an ER model, which are entities, relationships, and attributes. And on Tuesday, I'll pick it up by talking about how these things interrelate with each other. I think what I'm going to do is push the entire schedule at this point back by a day. So, because we have a day, if you look at the schedule, you'll see that the last day of class is canceled. I think just the way things are going, I'm going to need to push back. What I'll do is, right now, the last day of class is canceled. I think instead what I'm going to do is just push everything back. So you'll have the relational algebra quiz due today. The homework is due 1 day later, but I will push back basically everything by 1 day. Probably push the exam back now to the 16th of March. And I'll look at how I want to push back homework assignments. I may push those by a couple of days as well. So I will take a look at that. And once I have a new schedule set, I will release it. I know for a fact from past classes that this is exactly where I sometimes end up having to push a day. And what happened is because of COVID, we have 1 fewer day this semester than we normally have. And I thought, okay, the only way I can shoehorn everything in was to go with just 1 day for the DDL and subqueries. And I knew it was going to be tight. It was too tight. And I really needed 2 days. And so that's what happened. So any rate, the only quiz you need to deal with today is the relational algebra and relational calculus quiz. The homework is due tomorrow night. I know it's due Saturday at 6 a.m., so effectively tomorrow night. And then I'll look at how I rejigger a bit of the schedule and put a Canvas announcement out for that. So I'll let you go and see you all on Tuesday. There's questions.
Dr. BZ?
Yep.